Okay, well, we're going to get started. First of all, good morning, everyone, and thanks for joining us. My name's Tom Douglas. I'm with Raeco, and this is going to be our educational webinar on particulate monitoring. Joining us today is Sean Brantl. Sean's currently the Northeast Regional Manager for TSI, and he's also a former Raeco employee, so we're happy to have him back to help us out with this. We'll be fielding questions at the end of the webinar, so if you come up with any, on the right-hand side of the GoToMeeting box, there's actually a little chat box there. So as we're going through this, if anything pops into your head, enter it in there, and we'll address it at the end. Also, we'll be recording this, so if you missed any part of it or you wanted to share it with anyone, you'll be able to do so. So now I'll pass this on to Sean. Sean, thanks again for joining us, and put this in your capable hands.
All right, good morning, everyone. Thanks for taking a few minutes out of your busy day to get a little bit of a basic education on particulate monitoring, specifically some of the real-time solutions out there for particulate monitoring using a photometer-based measurement. Just to start, some of the areas that we're going to cover today is types of particulate, and by types of particulate, we'll be talking primarily about sizes, respirable, inhalable, and total, characterizing those and sort of how we can measure those. Why, in general, should we monitor or control dust? And that's from two specific areas that we're going to focus on. One is worker area monitoring and personal exposure monitoring, the other being more fugitive emissions and outdoor exposure monitoring, which is an area that we actually focus on most heavily. And we'll also talk about some industry examples where different photometer-based technologies have been used to measure concerns regarding community complaints, remediation, what have you. So those are the areas we're going to cover a little bit today. Just in broad strokes to sort of talk about in terms of types of particulate as a starting point. In terms of respirable particulate, we're basically talking about any kind of particulate less than 10 microns in size. These can typically come from nature, volcanoes, dust storms, even forest fires, to man-made, combustible processes like smoking, car exhaust, power plants, internal burning wood stoves, and even mechanical processes. We're talking about grinding of parts, maybe machining fluids, these type of things. The other size we're sort of concerned about is particles less than 2.5 microns in size, and what we do is we consider these to be the most hazardous from a long-term health standpoint. These usually we look at as fine particles. These can deposit deep into the lungs. They can pass through the lung tissue in a lot of cases and right into the bloodstream. And oftentimes anything less than 2.5 microns in size we would consider man-made particles, because that's the primary makeup of this type of particle. So again, respirable is anything less than 10 microns. Inhalable particles are anything less than 100 microns in size. These are going to enter through the nose, the mouth, during breathing activities. They're typically considered hazardous when they enter anywhere on the respiratory tract, but they're not going to be, typically the size is going to be too large to deposit deep into the lungs. So the body does have the ability to basically exhale those and get rid of those types of particles. For our conversation today, specifically we're talking about real-time photometers, keeping in mind that photometers typically have a cut point meaning the size of particles that can enter into the sampling inlet of about 10 to 15 microns. So really a photometer-based measurement is not designed to capture inhalable sized particles. That's going to be something you're going to want to use with a traditional gravimetric sampling analysis, but we can look at the respirable and fine particles. So basically, again, anything in the range of 0.1 to 15 microns, okay? Sort of just to get the discussion going a little bit, these are some of the particle sizes and some of the key things that we look at when using real-time technology. One, like we talked about, is environmentally natural occurring particles. These types of particles tend to be larger in size, a lot of inhalable particles, etc. What we're, again, looking at mostly is man-made particles, oftentimes from construction and mining activities, 1 to 10 microns in size, things that are easy to pick up with a photometer-based measurement. And a photometer, again, is a laser measurement. We'll talk about that a little bit more later. Some of the reasons why we need to monitor and control for dust. Number one, of course, is health hazards. Short-term health hazards from exposure to aerosols could be eye, nose, throat irritation, runny nose, sore throat, etc. This could be typical conditions reported for indoor air quality studies, or maybe offices adjacent to a manufacturing plant. Those are short-term things, not chronic, but certainly things to be concerned about. And then more long-term things we look at. You look at things like asthma, heart disease, bronchitis, reduced lung capacity. We also have increased mortality rates of lung cancer sometimes in areas that might be adjacent to a refinery or to a fracking type application. So again, there's a lot of concerns from a health standpoint about long-term exposure to different types of aerosols. Another big concern is risk of explosions, and that really is tied to combustible dust. Now what we're talking about today is a photometer. Photometers are not actually really designed to pick up a concentration that would be indicative of combustible dust, but what a photometer-based measurement can do is indicate if poor cleaning practices are, basically if you're not having proper cleaning practices in an area. As an example, if you look back, Imperial Sugar Plant was a major combustible dust explosion that took place, I believe, back in 2009. And that's a situation where basically, packing material from a forklift dropped onto a floor. When that packing material dropped onto the floor, basically what it did is it dispersed a large amount of sugar into the air, and with the spark created basically like a large explosion. And that explosion then triggered several explosions afterwards, and all the silos where the sugar was stored. So basically the learning experience is what you can do with a photometer for risk of explosions is tied to housekeeping. You want to make sure that you're cleaning up your workplaces. If you have fairly high ambient concentrations of dust in a given work area, then maybe you don't have good cleaning practices in the area. Obviously, from a capital perspective, equipment damage is always a concern, and that's tied to really that combustible dust. If you have an explosion, you're going to have a major loss of equipment and replacement costs. It also could affect the way that you're insured as a company. So those are things certainly to be concerned about. And then the other one that we see a lot of, specifically in the Northeast and in the West Coast, is community relation problems. Typically, in densely populated areas, we see heightened awareness by people in the community, activists, requesting that monitoring, airborne monitoring for dust, for vibration, for noise be done when anything's being done. It could be bridge work, it could be demolition of an old building. For instance, in Chicago, you've got the Michael Reese Hospital, which was demolished a couple of years back. Well, when that was demolished, there was airborne real-time monitoring going on the rooftops of several buildings in the area, specifically near schools, because there was a lot of concerns by the community that the demolition activity, if not done properly, would have some kind of an impact on the air quality, specifically for some of the children living and going to school in the area. So community relation problems often aren't tied to necessarily a standard because the levels are below what the EPA would dictate for your ambient air quality standards, but it's certainly an area where a lot of monitoring is done and an area that's really a good fit for a real-time device, like a photometer. So the two areas in terms of indoor monitoring that we sort of focus on when we look at exposure risk is work area monitoring, and typically work area monitoring would be mapping. Basically, maybe you have a machine cell where there's a concern about aerosol concentrations, and you want to basically take measurements from specifically where the employee might be working all the way out maybe 10 feet in every direction to see basically how those concentrations look at different distances from the actual work cell. And that would be, typically 24-hour monitoring, maybe for a few days or a week, to sort of get a comprehensive look at what's actually going on in that area. And then the other one is personal exposure monitoring. This is where you're going to use either something like a real-time photometer, the size of a sampling pump, to sort of get some basic information on what kind of exposure you might be seeing, to traditional gravimetric sampling with the 37-millimeter cassette. And ultimately what this all ties to is personal exposure limits, whether they are local OSHA standards you're trying to comply to. Maybe you have tighter internal standards. We see that a lot of companies these days, since the OSHA has not been updated for so long, are actually having much tighter standards internally and holding themselves to a much higher level of accountability than even what you see with OSHA standards. And the ultimate idea behind that is if you do see any kind of exceedance, the first thing you always want to do is try to engineer out the problem. So if you do, obviously if you see any kind of an elevated level, then you want to go ahead and try to implement whatever engineering controls you can. If you've run out of options for engineering controls and you see no other option, then the last step is sort of to put them into some kind of a respirator that's going to protect them from whatever hazard they might see. The nice thing about real-time based measurements is that if you take a sample with a gravimetric for 8 hours and you don't really see anything, maybe you see a little bit of an increase from one year to the next. You don't know what time of day that's happening, and the only way to do that is either to do a real-time based measurement where you can get a trend over 8 hours, or basically observe that entire workplace for 8 hours yourself. And since we're all busy, that tends not to be something people want to do, and so it makes a natural fit for real-time technologies. The two areas we're going to talk about, again, personal work area monitoring and outdoor perimeter monitoring. And this is what we want to talk about here is we're focusing this discussion today on photometer-based technologies. And with photometer-based technology, as we talked about before, the detection range for the measurement we're typically going to have is 0.1 to 10 microns. Okay, so that's the range that we're going to see particles within it. If we go below that, if you're talking about things like nanoparticles, ultrafine particles, a photometer-based measurement is really not going to be the right solution. TSI, the company that I work for, we do have a wide variety of real-time particle detection solutions. And we have technologies that go to ultrafine particles, but again, today with the photometer, that really is not something that's going to be the right fit. If you look across the board, photometers are designed in a lot of different ways. A desktop version is one that basically is designed to be placed in an area for work area mapping. This is something that you're going to run typically for 1 to 7 days indoors and basically try to get some trending of some workplace activities to see if there's maybe someone unloads a hopper at one point during the day, and when they unload that hopper you see an exceedance with that specific activity that then you can work to have an engineering control to remove it. So that's a nice thing that an area sampler does. And then the other one is a sample pump design. So if anyone's familiar with like an SKC company or Sensodyne, these companies make small portable pumps. Well, TSI and other manufacturers also make real-time photometers that are basically the same size as a sample pump. The difference is we're providing with a real-time measurement that corresponds to whatever activity you're doing. Also, with long-term monitoring, we incorporate something called sheath air. We'll talk about this a little bit. Sheath air is basically HEPA-filtered air that keeps our detector clean. So, if we're in high concentration areas, we don't want that contamination to build up on our laser and our mirrors to basically affect what we're looking at. And the other advanced sort of in photometers right now that we're actually actively going after is patented technology to do size segregated mass fractions. So typically when you're talking about a photometer right now, in the past, if you wanted to look at PM10, you'd have to put an impactor on your real-time instrument to look at just PM10. So basically we cut off all particles any larger than PM10. Same for 2.5, etc. So if you're looking at a specific work area, you couldn't actually get PM10 and 2.5 at the same time, and a lot of customers, a lot of people we work with requested that. So now with TSI anyway, you do have the ability to take real-time size segregated fractions simultaneously. So this gives you a lot more data about specific work areas, and it actually saves a lot of time as well. You can also, like you can with the gravimetric sampling pump, if you want to look at like ACGIH says, 4 microns is the cut point for respirable, then you can go ahead and use a cyclone, just like you could with a gravimetric sampling pump. And again, with an aerosol measurement, we're looking at everything from dust, smoke, fume, mist, fogs, etc. And what's important to keep in mind is that when you look at a photometer, we calibrate a photometer to Arizona road dust. Okay, every type of aerosol has a different chemistry. So if you're looking at welding fumes, if you were to put out a real-time photometer and just take a measurement, that gives you a representation of what you might see. But really what you want to do is you want to do some side-by-side co-located sampling of a real-time photometer next to a gravimetric sampling train. And then what you do is you set a correction factor inside the unit to tighten up your real-time measurement to what you actually are seeing with the gravimetric sample. So again, it's important to incorporate both gravimetric sampling and real-time solutions together. Okay, next we're going to talk about just a little bit of the operation behind what a photometer does. So right here basically what we have is a sampling path for in this case this will be a dust track DRX instrument manufactured by TSI. So what you can see on this is that we've got a sample that comes in through our inlet, and then what we're doing is we're taking a bypass off that sample and we're running it through a HEPA filter to clean that air, okay? Which then becomes what we call sheath air. Sheath air is HEPA filtered air, okay? This HEPA filtered air is then going to circulate around the sample that then is traveling down through our sample path into our measurement detector, okay? What the sheath air is designed to do is basically allow for us to take a measurement of our particulate without allowing the particulate to come in contact with our photodetector and our mirror. Okay, so basically what happens is we shoot a laser pulse through our particulate sample with a known intensity. Based on the intensity that comes back, that tells us basically the mass of that particle that we're measuring. Okay, and then in the case of our instrument like our dust track tabletop DRX, we actually pull that sample across a gravimetric filter, across our pump, and then out of the unit. The benefit of that is that basically with that gravimetric filter in place, you can run a real-time sample with a photometer, then also collect that sample on a gravimetric filter for analysis by a lab. So again, this goes back to the correction factor idea. If you're measuring for welding fume, you want to make sure that the real-time measurement is as close as possible to what a gravimetric would provide you. You want to run the gravimetric filter, take that sample, send it to the lab, and then set corresponding correction factors. Right here, work area monitoring. This is just talking a little bit about assessing the work area. You know, different ways to do it. You can walk through with a handheld instrument, which is typically what you want to do to identify hotspots. Example of this would be, we work a lot with GM. Every year they go around and they do a mapping study of all their machining cells. They're looking to find out if there's any kind of exceedance for oil mist specifically, and they've been doing this for 20, 25 years. Every year they take samples at specific points to identify if there's been any changes or anything happening to their engineering controls that would indicate further evaluation of an area. So they take a 10-second sample at various spots, which is something you couldn't do and really get any kind of accurate information without a long-term study using the gravimetric type approach. Area assessments, this is another common area. We work with Detroit DTE Energy, and what they do, they use real-time photometers to measure around their coal conveyors, and what they do is to justify the type of dust suppression equipment they have in place. For instance, they did a study where they had vacuum-style dust collectors that they did not feel were very adequately removing dust. They wanted to move towards a misting type machine. Basically, the mist agglomerates with the coal dust, settles down onto the ground. So in that case, they used dust to document what kind of exposure was in place prior to going to the misting machines, and then they also documented what the exposure looked like after moving to the misting machine. So a lot of before and after characterization with that. Personal exposure monitoring, again, we want to put the sample in the worker's breathing zone, which is going to be right on the lapel right there. Typically that's going to be within a foot of the head. And in terms of sampling, again, we always recommend, gravimetric sampling is certainly important, and that's what you're going to use for compliance-specific sampling. If you've identified an area that is within compliance, but you still think there may be some kind of a concern, maybe there's a new process adjacent that you think might be causing some dust to mitigate into the area that's within compliance, and that's a good time to use something like a real-time sampling device. You know, why is real-time monitoring becoming so popular? I think the biggest one personally is, I mean, lower cost of ownership is certainly important. You don't have to wait for a lab analysis. But I think what's most important, it allows for trending over long periods of time. So a lot of times now, a lot of work areas like we talked about are below maybe a Pell level, but there still could be things that could be improved in that area. It's very hard to identify that with a gravimetric sample, again, because you can't see what's going on minute to minute. With a real-time monitor, we do graphical trending, analysis. You can do 15-minute average, 1 hour averages. You have a lot of ways to look at the data and see what's going on. So I think that's the most important thing that we offer with real-time measurements. Common things that we tend to measure right now, I would say indoor welding is definitely our most common application. We've worked quite a bit with Lincoln Electric. Lincoln Electric has basically designed their work cells and their training centers around using real-time photometers. So if they're trying to address what types of exposure they have when they're going through welding training school, to show them where they should be doing the weld, if the downdraft exhaust is working right, they implement real-time photometers to basically provide that feedback to the welding operators. And sort of the area where we see the most focus now would be perimeter monitoring. This picture right here is just an example of our solution for outdoor monitoring. What you see here is what we've done is we've taken a Pelican case and we've retrofitted it for outdoor monitoring. On the top of this case you have an isokinetic probe. That isokinetic probe allows for a sample to be pulled into the Pelican case without any kind of water or anything entering into the enclosure. And then on the left side right here we have a radio modem. So what that allows is communication back to a main hub where an operator can actually see the data coming from this monitor without actually having to going out to the unit to see what is happening. Inside the box right here we have a little water trap, so if there is any kind of little water that gets inside this enclosure, it gets trapped in this little water trap, and then we pull the sample across through this tube across to our dust track and we take our measurement. A lot of applications we work with. We work at landfills. We work at construction sites where there's not an easy access to power. So in this case, what we offer is solar panels. Solar panels feed our internal battery system that we offer in the unit. These are the two batteries right here, and actually keep a charge on that so we can do 24/7 monitoring throughout the year. We're seeing a lot of our projects now require that. Okay. The reason we're doing fugitive emissions outside is typically we're compliant to the US EPA under their national ambient air quality standards. For instance, under that standard, 24-hour US EPA dictates you have to stay below 150 micrograms per meter cubed. Example of doing this, we worked recently at University of Washington. They had a demolition of a hall that was adjacent to a children's center, and they were really worried about basically if there's going to be any kind of dust mitigating near that children's center, again concerned about the exposure to children. So what they did is they used dust tracks. They set them up around the perimeter of the construction site. They did 8-hour sampling during the day, during the heavy construction activities, and they did overnight sampling to show if there's, basically the offset between sampling during construction activities and sampling when there were not construction activities going on. In that case, they're able to correlate the construction activities to not have a significant increase to the ambient air quality, which is good, which is always what we're hoping for. So there are a lot of applications like that. Typically what we're going to see on a perimeter monitoring application, we're going to do an upwind and a downwind measurement, at least 2 points. That way if we've got, what we want to do is calculate the difference in concentrations from upwind and downwind and get a comprehensive look at actually what's going on the site. So in this case right here in the top, you can see we've got different measurement parameters, upwind and downwind, based on what we know is the wind direction for this project. And this shows here, it's pretty small, but basically this shows the data that we would be seeing at PM 2.5, upwind and downwind. And again, this is stuff that this site is going to provide to EPA to document that they don't need to do reference method sampling. Because again, a lot of times what we're doing with real time, we're referenced to EPA, but we're not going to be what's actually reported under the regulations. Okay. In the absence of time, I did want to show you guys a couple products that we're working on right now specifically. This here is the Tappan Zee Bridge. This is a bridge, New Jersey to New York. And what we've got right here is basically this is a community awareness project where the community was requesting out to the mayor of New York that during this bridge project, and what we're seeing here is we're building a new Tappan Zee Bridge, and there's going to be the demolition of an old bridge. So there's concerns about asbestos and things from sandblasting, silica for the old bridge is going to be taken down, and then there's also concerns about any kind of impact from the new bridge being built up. So right here what we have is 4 different measurement points. Okay. Typically what you're going to see on a project like this is we're going to have downstream, downwind measurements that we're going to compare to a base station. And what we're just doing, what we're really looking at is to see if there's any kind of excessive particle concentration. So I pulled this data from a few days ago. I believe this was during a heavy rain activity. That's why I see a large spike in our concentrations right here. But basically what this allows is any member of the community can go on to this website and look at particle concentrations over time as well as noise and vibration. And this is not tied to any kind of US EPA regulation, but this is really tied towards community awareness. People want to know what's going on, what the air quality looks like. The dust track provides the data in order to do that. This is another project that recently has had a fair amount of interest. This is Tide Marathon Oil Refinery. Basically in this case what we've got is we've got coke piles that are used by the Marathon Oil Refinery along the Detroit River. Challenge is that these coke piles are not regulated by the state. But again, you've got a lot of complaints by the community. When the community sees any kind of airborne dust cloud, they want to know what's going on. There's a concern that it's affecting their health. In this case, there was a state official that came down and observed the dust, noted that sampling had been done, and that they were below levels, but that really did not put the community at ease. And so what happened is they had to really go in and deploy real-time measurements by the EPA, really to justify that there wasn't any kind of a threat from a personal hazard to these blown coke piles that they're blown across the riverfront. So again, community awareness projects is really driving a lot of the work that we're doing these days. People, community in general seems to be much more aware of what's going on with the nature of the indoor air quality or the outdoor air that's around them. They want to have data to sort of show them or support that there is no kind of a concern. Another area that we get into, this is an iron ore mine. And what we're seeing from a lot of mining customers right now is that, again, what they're using real-time photometers to do is to set thresholds that are well below what would be considered an excursion by the EPA or any kind of other regulatory body. Because typically a company doesn't want to be visited by the EPA. They want to be proactive in their approach to monitoring their dust. They want to make sure that they're preventing any kind of visibility that would be bad for their company. So in this case, and what we see a lot is you've got a 24-hour monitoring station set up all around this mine. They do a lot of blasting. They're looking at annual averages, and what they're also doing is they're doing short-term 15-minute averages specifically during the blasting. So if there is an excursion that happens, then they can go in and basically take some kind of an engineering action. It might be doing a spray down with potable water. It might be increasing some of the ventilation controls that they have in place. So a lot of times, again, when we think of photometers, we think about they're really good screening devices. We always say that a photometer is very precise. We're going to provide very strong repeatable data, but we're not always going to be 100% accurate. And to get the most accurate, you're going to want to do gravimetric sampling. And again, when you're out there in the field, these are just some areas where if you're seeing these type of things, might be an application for using a real-time device. We've got construction activities, tearing down an old building. We've got cutting of bricks, which is certainly a concern. Silica. We've got we do a lot of roadway construction work, roadway monitoring. If there's any, around Chicago with all the roadway construction constantly going on, we're doing a lot of ambient monitoring there to assess what kind of air quality we see. And then we've got some foundry work going on. So we find ourselves in a lot of applications. At TSI, we always say we're about a mile long and an inch deep. We've got a million different applications that we sort of find ourselves in, and we implement specific particle technologies to address and provide feedback to our customers. And that's it.
Well, thanks a lot,
Any
Sean.
questions?
Yeah, like mentioned, if you use that chat box, if there's anything that pops into your mind that you'd like answered, or even offline, we can answer you as well.
And this was meant to be an overview. We can certainly get into any kind of more detail if you guys would like. I'm just trying to provide some basics as a conversation point.
Yep. All right. Well, not getting a lot of questions coming through, so with that, we'll wrap it up. So appreciate again taking your time, Sean. Appreciate everybody that dialed in. Hope you guys found it worthwhile. Again, this recording will be available on our website at Raeco.com. If you have any other questions, concerns, you can email me at tom@raeco.com. And thanks again, and have a great day.